not the hand waving stuff. One thing says, gee, it doesn't, I don't think people read the book or something like that. I mean, it's actually, oh no, it's kind of like washing one's hands after going to the bathroom. 90% of people say they do, about 65% actually do. And any pollster will tell you that one of the biggest problems with polls is that the people being polled will generally try to give the answer to the pollster that they think the pollster wants to hear. Huge thing. I mean, a lot of studies, a lot of effort put on defeating that, because it's exactly what the pollster doesn't want. Makes the polls invalid and they don't get paid for it. It's not of any use. So the one looks for ways of telling what's happening with this type of things. But unless one depends upon people's answers directly, the better off usually. So right enough. In any case, it's usual bit. You've heard that. Mr. Collins come here, but I guess it was you with the pencil, because he came from your area, I'm guessing. But it really applies to everybody in the class. It's amazing how many people show up with a laptop, a pen or pencil. It's like, well, how do you write data down without a pen or pencil? USB sticks, because computers get swapped around. Computers get tied up by other students. We have failures. We have reloads of software, and stuff gets erased. I move computers around a bit sometimes. I have had semesters here, like the PLC area, where I did a weekly shuffle of PCs, just simply to pick out which 8 were working that week. So in that type of environment, people would leave the programs on there, almost guaranteed they would not get back to it the next week. So I mean, it's what you do have control over is your USB stick. That you have control. You pick it up, you take it with you. You still have a backup copy on that PC, so to speak. It's not a reliable backup, it is a backup possibility. You still have your USB stick you can carry with you. And with a USB stick, what can you do? Get in the habit of downloading your PC at home as a backup. For me, I have copies of Beyond Compare for all the PCs I deal with. It's an old bootleg copy that compares 2 data structures, file structures, and computer, it matches them. So it copies the differences, one way or the other. I use it a lot because it actually copies files, massive file transfer dumps, faster than Windows does, which is pretty impressive. So I mean, there are utilities like that. If you sit there and say, I got this USB stick, I got this USB stick, I got this USB stick, they're not coordinated. Because most of us do a lot of computer work at that point. And something like a file comparison program like that, and Beyond Compare is one. There are others. Some are freeware. They can do this for you, look at the dates, look at the differences, and give you the differences, and let you copy back and forth. They can automatically do it, or they give you manual choices, or a mixture to do something like that. So you coordinate, get yourself down and say, okay, now I know this is it. Because I know over the years, particularly at work, when it eventually gets to the point of saying, gee, is it this file, or is it the one on this, or is it one on this one that I want, or do I want a combination? So this is a way to get around that. In any case, enough of proselytizing or whatever things. Welcome back to Process Control, P&ID. And it's kind of one of the 2 things to get out of process control ultimately. Documentation, what's the type of documentation look like? And P&ID is it, realistically, the head part of it. And calibration, as opposed to just typical maintenance of, seals are blown. Mechanical install class does a nice job of bearings, seals, some of the coupling stuff, and drive systems class will have a little bit into that. Really, mechanical install will be the class really will take care of that. Jacking pumps, that sort of thing. But the concept of calibration, which might be a perfectly valid working system, versus jacking something that doesn't work. Calibration will be used to identify problems, and it's also for tweaking stuff to make it better. It may be okay to use, but could be better, tweaked, more in line, more linear. And that's where this gets into process control. That's a target, really, process control. Above this, designs of these systems, that's really more of an engineering type of thing. And that's not really a direct worry of yours. A little understanding what goes on is one thing, but really, at this point, it's more calibrating loops, because that is something that you will do at work, is calibrate components, calibrate loops. So that's where we're heading. But for right now, a little bit about P&ID. Today, rather than me talk and chatter again, I'm just going to use two company sites to go over P&ID diagrams, kind of an overview, so you get to see how they think of it and talk versus just me. This is from a chart manufacturer who actually makes the tools for making these. The other one is Corso Systems, is another company that's more involved with the drawings. But what is a P&ID? And here they refer to as piping and instrumentation, as opposed to process and instrumentation. Both are perfectly valid names, depending on the company. So what are they? A P&ID shows the piping related components of physical process flow. Most commonly used in engineering field. That's a sentence that works. It really shows the instrumentation of the control of a process. Probably another way of saying it more directly. And that's why it's a piping and instrumentation. There's two halves. There's the piping, the connections of things like tanks, valves, pumps, and how they're tied together. Much like in a schematic, you'll have resistors and power supplies and motors and contactors, but the lines connecting them, the wiring, is the connection where the electricity, the current flows between device and device. Here, pipes are where the liquid material flows from a tank to a valve to a pump to whatever. That's assuming a liquid flow. Could be an airflow. We could have material flow, in which case material flow, if it's solid, most likely it's not a pipe, it's going to be something like a belt to move it. Or people. I like that, a people.
A people.
Could be a person, could be multiple people. Persons, people. To hand walk it through. That's again part of the process. Instrumentation is the important part of this particular type of diagram, because it shows where the measurement and control aspects are involved. Process flow diagrams don't show that. P&IDs do. That's the addition to a PFD to make it a P&ID. So graphic representation, piping and instrument details, and even then, when we refer to piping and instrument details, not really. A P&ID doesn't have to say the size pipe or material of pipe, it just shows a pipe. Now it might show a heavy line for the process, it might show a light line for the control or measurement. It might even differentiate between pneumatic and hydraulic lines and other control and measurement lines. That's as far as it gets. What gauge that wire is, or what size the pipe is, usually doesn't dawn those. Control shutdown schemes, it will to a degree, but not again. It takes other documentation where they say, how do we control it? How do we do shutdown? It basically just shows what devices to go to. Like if I needed to turn off a system, I could use a P&ID to identify, okay, that's the hand valve I need to crank on to turn off the flow of whatever. And I look for that tag out on the floor. When I find it, that's when I turn off. To that degree. Really doesn't really give a whole shutdown procedure. That's a separate procedure. Safety and regulatory requirements, not really. Even basic start operation. This is stuff that's really more peripheral in there. It's a schematic, it's an illustration. Automation is really the automating of control and measurement. We could do it manually, but it's most likely automated to a large degree. That's the important part of it. And you see increasingly it's automated. It's a big word, automation. And what's the difference between a process flow diagram and a piping instrumentation? Simplified conceptual designs, process flow diagrams. Fewer details, first step, more of a bird's eye view. Realistically, more tightly, the process flow diagram shows the process. We add instrumentation to that to make a P&ID. Now it means a process flow diagram, what it doesn't have, it won't have instrument tags. It really does have block functions, and usually it's assigned as blocks. They may or may not show a symbol for a pump or a valve. Don't really have to. When we get the P&ID, we do have the symbol, the typical ISO symbols for those. We definitely have the instrument tags, and we have the instruments added. So if we're measuring, if you have a tank and we want to know the level in it, that level sensor probably is not in a process flow diagram. I wouldn't say 100% it's not, but most likely it's not in there. P&ID is 100% in there. It shows the measurement, it shows the control. Process flow does not show how it's controlled or the thinking process of what needs to be controlled. It just simply shows a process. Limitations, like any other schematic, your basic limitations are, it doesn't look like what you see on the floor. When you see a valve in a P&ID, it looks like a butterfly. It looks like the cross with two ends covered. I've yet to see a valve look like that. That's not the intention. The thing is about pictorials, and we've seen pictorials, and almost all of us want to use pictorials for everything. When you begin with, you have 3 connections to make. Pictorials are fine. You see a pretty picture, you see a line draws here, and you kind of duplicate that line. When you're down to 100 lines on a picture, it's hard to differentiate. It starts to look like a big block on the paper, all filled in with these 100 lines crisscrossing each other. It's impossible to see. So it's not really useful. The thing about pictorials, it shows me a lot of information I don't care about. Like, do I really care about the color of a valve or what it looks like? Beyond identifying where the port is I need to connect to, or where I need to screw into, or the handle location, I don't need to know that. And even then, to make a connection of a piping, I don't really need to know where the handle is necessarily until I'm actually installing it. At that point, I have the valve in my hand, I can pretty well figure it out. So those don't go into diagrams. What's important in functional diagrams is the function. So when I have a P&ID, I need to be able to know where the control devices are, where the measurement devices are, and be able to reference something, so when I look at how this is calibrated in a loop, what parts I'm worried about versus which ones I'm not worried about. It's like the fill-in, this is where it gets subloops into. If I'm trying to set a rate of flow to fill up a tank, and I have ability to control the flow here, and I can also have, basically also the ability to do the tank level as well. If I want to fill up tanks at a certain rate, I usually calibrate the flow first. Maximum flow, minimum flow. So it does imply that I worry about calibrating this part of the loop first. Then if I'm worried about the tank level, achieving that, I calibrate that second. I split it in two different calibrations for system. The reason being is I can go back and forth. If I calibrate this first, it still doesn't take care of the flow, so it may fill this in too fast, too slow, whatever. The overall loop doesn't optimize getting this level of what I want to. So really look upon this as a component of this overall loop. Overall loop being the measurement, come back to a controller, that forms a closed loop, just like the flow. If I put a flow meter here, or even estimate the flow, more like it, that's a separate loop. This is a case where I want to be able to break that down. Now, it's easier to see if I have it on PNID like this. I can identify definitely two loops. This overall loop might be 100, in which case the flow loop here might be 101. F for flow, L for level. Something of that order. And this is concentrating the flow, where I worry about an estimate for how fast or can I fill up a tank, and then the filling up the tank afterwards. This might be adjustable too. This isn't, but probably is not the entire system, but just a part of it to show that this is why we have subloops. Is in tuning, we usually want to do the component, subloop, the bigger part of the subloop that incorporates that, treat like a low level of components. It's a layered approach. A lot of big processes are complicated. There are multiple little loops. And tactics go bottom up as far as calibration. Because for a component to calibrate a valve, like a diaphragm valve, it doesn't really matter what part of the loop it is. That's not going to affect that valve operation. So do that first, get that optimized, working. In other words, I've unplugged it, unclogged it. The bladder's working properly, that sort of stuff, maintained, it's not leaking, because that affects things. And once that's a perfectly working one, then I work with a small loop here, which in this case would be the flow rate measurement, to make sure I have that correct. And then once that's corrected, then I have a reliable flow that's optimized, and I can worry about what level I get in the tank. But as soon as I worry about the level in the tank, and then recalibrate the flow rate, I might improve the flow rate, in which case that level's getting filled faster than I expected. Possibly, something else might be going on as well. But you don't have the reaction time for the level. That a faster flow rate that's unaccounted for might fill the level of the tank too fast. Later on in the course, when I talk about calibration of loops, we'll see one of the big things is called lag time. Is to make the decision. A quick example of that. Have you ever had to go someplace and rely on somebody sitting next to you in a car for directions?
Yeah.
And it's like, turn here, turn there. And what happens if they're late telling you when to turn?
Missed the turn.
You miss your turn, right? That's the epitome of loop performance. Why are control systems not perfect? And a big overrunning thing is this concept of lag time. If you got your directions ahead of time, every single time you drove a car, it'd be very easy to get to your target, wherever it is. But if you get to those directions a little late, like turn there type of thing, it's very easy to wind up going extra blocks. The longer that lag time, the worse it gets. Talk about overshoots and undershoots and all kinds of stuff like that. Driving around the block is kind of an overshoot situation. You overshot where you needed to go, and you have to make a correction for it. That's part of process control as well. And so I'll put that in the back half. That's really what you're trying to reduce and calibrating loops. It's that sort of thing. Same thing here, and that's why we usually do part by part, bottom up. I'll jump over to this. PNID drawings. Of course, those systems and process, the basics, just a lot of this is review. Example of a drawing. This is a nice, cute little example. How many subloops are there in this drawing?
Subloops.
Three. I see a 100. I see a 101. I see a 102. So already this is a little bit more complicated than I've been drawing. And what's the process variable for loop 100? Level. What's the process variable for loop 101?
Pressure.
Pressure. And more specifically for nitrogen. And 102 is for temperature. Most likely, you have hot water here that's stored, some nitrogen that's put in, and some vent to it. We also have a heating pad as well. Why nitrogen for pressurizing? And this is what this is doing. This hot water storage is storing at a certain temperature,
It cools.
a certain amount of water at a temperature, and pressurized. Of course, why would you pressurize water? What does it move it? How do you move it against gravity? We need a force. What's the built-in force for water? Water pressure. It's kind of like when I turn on the faucet in the kitchen at home, why does water come out? Water pressure. There's no water pressure, I'm not getting any water out of the faucet. Unless, of course, there's a source of water above that faucet, literally above the faucet. But that's where the pressure comes from. So you need pressure. And why nitrogen in this case for pressurizing the water? So many people remember this from my MT 131 class. Or Mr. Collins hasn't beaten this into you yet?
Okay.
I'll tell him he needs to beat this into you. Remember the ideal gas law, pressure, volume over temperature? And you have pneumatic and hydraulic processes, and the big difference between the two flows, besides one's wet, one's not wet. Liquid is known as constant volume. Air is known as constant pressure. Okay, a symbol of that. If you have a balloon in your hand and you blow it up, I taught the class used to give people balloons. And they blow them up, and you go, you get this nice big balloon all blown up here, tie it off. What's the air pressure in that balloon?
I don't know what air you put in.
It's gonna vary.
The volume of the balloon.
That's not pressure. What's the pressure inside the balloon? You play with the balloon, you bounce it up and down. It's 1 atmosphere of pressure. Now it's not exactly, there's a small, slight differential. Think of it this way, you have a big balloon that's filled up. What do you know about the surface area inside that balloon versus the surface area outside that balloon?
It's wet.
They're about equal, aren't they?
Yeah.
Right?
Wow.
Not exactly, but pretty close to it. The bigger that balloon's blown up, the less the differential. Well, so the surface areas are the same. Now, if the balloon's staying still, are the walls going in or out or staying still? They're staying still. What does that mean? That means the sum of the forces pushing out on the balloon equal to the sum of the forces pushing into the balloon. And most of that force is pressure. Force equals pressure times area. So if the area is roughly equal, the force is roughly equal, the pressure is going to be equal. You have 1 atmosphere of pressure outside the balloon, so the pressure inside the balloon is the same. Now, if your volume goes down in that balloon, like you push the balloon in, what happens to the pressure inside the balloon?
It goes down.
And it increases because pressure times volume has to be a constant number for the same temperature. That's the ideal gas law. So you push in, and you have a smaller volume, it creates higher pressure. Now, of course, when you untie the balloon and let it out, why does the air escape?
Because it's elastic.
Because the elasticity has a tendency to collapse in. That's a little bit of difference between the air pressure in and the air pressure out. So balloons, from a ideal standpoint, if you have exactly 1.000 psi in the outside of the balloon, it's probably a very small smidgen inside bigger, higher, because of the elasticity of the rubber and heat difference in the area. That's so ignorable for all practice and purposes. We ignore it. There's other things we ignore that are far more, that make far more difference. That's the concept again of just think through that. Now here, why nitrogen? If you pressurize, you can pressurize nitrogen because again, it's constant. Well, it's a constant pressure. I can jack that pressure up. Now, if I have a certain amount of air here and I put more water in, what happens to that air? It collapses. So when I have a certain amount of nitrogen and water in here, if I put more water in, what will happen to the water? It'll occupy more volume. So the air molecules have to collapse. They collapse. As they collapse, they exert more outward pressure. That's how you get pressure built up. Accumulators in the hydraulic system work exactly like that. You got a bladder in there, air trapped in, you jam more fluid into it, it creates more pressure. In fact, it's one of the ways your water pipes break. You have things like trapped air inside a water pipe, and the ice comes into it there, starts to push the air into it, finally it creates enough pressure to blow through the copper piping or PEX piping. So this is used to pressurize the system. And here, if the pressure is not great enough, what do we do? Well, let's look at the pressure loop here. 101, what do we have control? We have, for pressure, we have three instruments, don't we? Initially. Actually, four instruments. You see a PY there as well. Here, everything's called a PY, which is probably not the greatest thing in the world. These are what? These two devices are,
Same.
they're the same device, but what is that device?
Converter.
IP converter. Right, when you have a diaphragm here, you need air, the electrical signal, converts electrical signal to air to control these diaphragm valves. So they're IP converters. This is probably where we measure pressure. You know, it's called a Y, not a T. I'm surprised the 101B versus 101B. That's not good. And I have a hard time saying what PY 10B, 101B. So that's a mistake in this drawing. This is probably just a PT. Is what I would really guess it is. Because something has to measure the pressure for that controller, the PIC. That's your controller of the system to generate this. Now, things to note here. The IP converter, the pressure sensor are all mounted where?
On the device.
Basically around that tank. By the way, if you guessed by now, this is the tank. Where is the controller?
Primary location.
Somewhere else, probably a control panel someplace. And does the solid line means can an operator see it?
No.
Most likely. And as notice the PIC, I for indicator, so it has some gauging that an operator can see as well as do direct controlling.
We got the wrong one.
That's our pressure. So we have two valves, one going in, one going out. So we control both more gas going in, we control if there's too much gas, let it out. You probably need both to get a certain fixed pressure in there. Now again, we have here It's hot water storage. And notice the two valves in here. Something we know about here. V1 and C, V2 and C. What does that mean, do you think?
On the clothes?
Normally closed, very good. Normally closed valves. So this is a storage tank. Ordinarily, you don't have liquid going in it. You put the liquid in it, store it up, keep it. When you need it, that's when it goes to users. You know it's users because the tag says it's to users. To operate the temperature here, how is this done? How many instruments involve the temperature control?
Two.
Two. TT is what?
Temperature transmitter.
Transmitter.
Temperature transmitter, that's your sensor. Basically measured, based on like a thermometer for electrical stuff. And it's electrical signal. This goes to a controller, and it just directly turns on the heat pad. This is not the power for the heat pad, it's probably separate, but this is the control signals they turn on. These tend to be control signals. Again, that's mounted in a panel someplace where an operator can see it. Most likely the same panel that the pressure indicator controller is mounted. Lastly, level. Now the level here, notice that we have, this is an interesting thing on the tag. We have an LG2 and LT100. If you were to rewrite these tags, what would you most likely put in for LG and LT?
A and B? Well, no.
D. LDG, LDT. Differential. Why do I guess differential? I'm looking at two connection tubes. So it's probably getting the level difference between the bottom and top. You might use pressure to do that, I don't know, but in any case, this is a level indication. The 100 loop essentially, and this just goes to
Indicator.
an indicator. So is there any control here directly on a level?
No.
No, it isn't. My guessing is that it's a hand valve job here. Let water in, hand valve or so go out, or at least manual control. That's not ordinarily exercise. So the only thing we're really doing here is just saying how much water do we have. And the fact that it's just simply an indicator means it directly tells a person how much water. So an operator makes a judgment when to let water in, when to let water out. So it's probably a manual procedure. It's like, okay, we need to refill the tank. Operator comes in here like a bathtub, turns on the spigot, turns off the spigot when the indicator says level's high enough. And it sits there in stores, nitrogen comes in to keep it pressurized, temperature heat pad keeps it warm until it's needed, then the operator turns it on again. And notice that all the indicators, temperature, pressure, level, are all remote. They're all basically operator panel, control panel. So that panel is probably not right on the tank, well, it wouldn't be on the tank, but some operator panel. Same panel, I'm guessing, because it's one solid line, so it's the main panel. There's no remote alternative panel, no auxiliary panels. Between the temperature sensor, which is the LT, going to indicator is a remote indicator. If that indicator was built onto the LT, it'd probably say LIT. Or just LI because it would need a transmitter. Those sensors are usually called Ts, transmitters, if they're sending electrical signal to an alternative indicator source, indicator sync, so to speak, or controller. Their LIs are direct indicators, like a thermometer is a direct indicator. That's how you read this. So you can see 3 loops, you can kind of guess how it operates, right? We talked through how this operated from this diagram. So this diagram gave us a lot of information. What sort of it tells us where the instruments are on here. It tells us what the operation of this is, without ever seeing it before. I've still yet to see the hot water storage tank. I have no idea what the size of it is from this thing. That's true, I don't know the size. But I can pretty much guess a lot of what it's used for. And it's not a whole lot to this drawing. It's a pretty simple drawing. It's almost stick figure. That's what schematic should be. The information that's useful, and stuff that isn't, don't need to see it. It's like fallen trees in the Amazon. I don't know it, I don't care, I don't see it. I guess I can always put on YouTube and look for a channel that shows me live trees falling in the Amazon, but I don't even know that exists. That's basically the guts. You know, in a quick 15 minutes or so, what a PNID does, how to look at it, just did an exercise, and how to get information from it. Yes.
Shouldn't that, the pressure converter, you have 3 in the line, shouldn't it be A, B, and C instead of D?
If this were the same instruments as these, then that should have been a C. Then you have a device, B device, C device. If all 3 were IP converters, and that means this would be air here, with some going to here. I don't see why we would be injecting air into here. We have nitrogen to inject and relieve. I'm guessing this is a sensor. So I think the mistake is this should have been a PT.
Yes, sir.
If it's a PT, I would not necessarily put a B there. It'd be 101, that's enough. If there were a second pressure sensor, then a 101A, 101B would be appropriate, versus the PY, 101A, 101B. That's a good observation. As I said, that is a mistake in this drawing. To me, it's a mistake to label, for one thing, you should never see 2 tags the same. Sit there in a parts list, which is which. You know, it's unique names. It's kind of like if we ever had 2 students with the same ID number. In a school here, we'd be forever mixing up your academic records. Forever. And that's not good. Yeah, it doesn't serve the purpose. It has to be a unique name. The instrument tag has to be unique for each device. It's 1-to-1 between the tag and an instrument with its location. It can be, you know, we have 5 of the same model, that's fine. Somehow that tag differentiate. And worst comes to worst, we run out of differentiators. The little letter on the end of this 101 is exactly how we do it. You'll see this on the floor as you work through the laps, you'll see a couple devices, usually hand valves, where the literally are about 3 or 4 hand valves, and they're separated by a letter after the end of the loop number. Now, if the loop number is different, that's sufficient. If the loop number is the same, it's like HV 100. I think it's an A, B, and a C. I think. Then it has to be differentiated that way. It does have to be differentiated. Now, in a parts list, what you'd see here, if we were doing a parts list on this, the documentation. Actually, I'm going to put down manufacturer. About 100 for some reason. One line item is sufficient to cover all those instances if they're the same IP converter. Dayton IP42, IP converter. Notice there's two references here. So there's two places would appear here. And those references refer to the instrument tag. And why the reference is because this is unique. Because usually I look at this, say I need to replace an IP converter. I know I have to replace this one. I look at the instrument tag on the device itself. That's all I really have. I might have a nameplate, maybe not. Usually I don't, it's a small part. But I definitely have the instrument tag. If I have the instrument tag, then I can go to here, and that's what I buy. Get a purchase record company, write that up. Now, when these things are several $100s, I use a purchase record to buy it. It's like $100. Usually just go ahead and buy it and submit an expense report. Now, what's the difference between the two? Back in the day, when we used to have to do this all the time, purchase recs, back 30 years ago, used to take $75 to process in the company. Expense reports like maybe $10. So they didn't want to sit there and buy a $50 item using a $75 paperwork form. So it's always, go buy it, expense it. As engineers, we generally did that. It's a huge item, really monster. There's a lot of money involved there. That's the purchase rec doesn't matter that much. Go write the purchase rec. You can do a lot. Anybody works in these companies, not many times you wind up with saying, I need a bunch of butt slices. I need a wrench. The fastest way to do it, usually just buy it from the store, Home Depot, and submit the receipt and expense report. And nobody really questions it because that's a much cheaper process than the purchase rec is. So actually, a lot of companies encourage that. Now, of course, you try to do that with your 65-inch TV screen for home, but probably get a little bit of a look at it.
I saw 90 the other day.
That's how you do it in the parts list reference. The reference is what gets you the tag to what the part of the manufacturer is. Then if you need just documentation on it, you can take a Dayton IP42 and look it up on the internet. Like for instance, I put IP42, what comes up? In this case, it's not an IP converter. It looks like it's a push-to-test pilot light. But if that was the way it actually came in documentation, I'd say I need to fix my documentation. Because that part number is not going to work. I've run across those before too in companies. You get a lot of that in obsolete parts. And almost any of you work in a factory that's been out there for a while, like 5 years, 10 years, guarantee you're going to run across obsolete parts. I do it on the stands we have out here. So I mean, that's kind of how you go about your business. What they include. Mechanical equipment named and listed numerically. And when we buy mechanical equipment, IP converters seem an awful lot electrical and they still consider it mechanical. Just a physical part, component. Anything like that would be mechanical. Valves, process piping, sizes, identification, could on the drawing have listed in a note the size of a pipe. I have seen that, but it's not guaranteed, but I've seen that. None of the examples I've shown you have extensive notes like that. When you get around those extensive notes, it really fills up the P&ID fast. You get these huge things, lots of things going on. We'll see examples later on. I'm gonna say, that's a lot of stuff. For a first time look, which is what this course is, you don't necessarily show you everything. It's kind of like learning how to swim, and they take every one of you and throw you in a river. Usually better do it in a swimming pool, so that the couple of you that go down to the bottom can still pick up, bring up top. We throw you on the Savannah River off the I-20 bridge. That may not be an option.
It's the impact.
Well, to tick off Mr. Collins enough there, he might be tempted to sit there and go, we're learning swimming today, folks. If he does that, be aware, be careful. Permanent startup flush edges, flow directions. It does show the flow, that's process flow diagram part, shows you which way it flows. It references the connections, interlocks. A lot of these are little details in here. Those are usually notes. Something you wouldn't confuse because you have no idea what a pit is. P&ID, process and instrumentation diagram. Notice it didn't say piping process. You'll see both. Neither is incorrect necessarily. PID stands for proportional integral derivative. We'll get to that probably in the last month of this class. Heavily into loops, and then what are the types of loops. Get into it, I think around lap 9, lap 10, but the back part of this course will cover that. It really is not part of this, how to read this, we've been through it. Of course, identification letters, you can see example. I like the common examples, there's really more what you're gonna see. Flow control valve, F for flow, and then CV for control valve, LCV for level control valve. Notice you're used to seeing LV, FV, and here we put a CV in there. So this is more an example of this company. That ISO standard wouldn't have the C in the control valve. Notice the C is not modifying the flow, it's modifying the valve, in a sense. Pressure transmitter, level transmitter, temperature transmitter, pretty easy to see. Level alarm high, level alarm high, high, low and low, low. That seems kind of ridiculous. I mean, you're sitting there saying, is there going to be a level alarm high, high, high? Which almost sounds like a bad Paul McCartney song, but that's a reference to Lost in the Note. No, you all, none of you are old as me. But the concept of 2 highs versus 1 high is how high is high type of thing. Usually what you mean by that is level alarm high would be a case where you'd say you're starting to hit the top. It may be a normal occurrence, but you're still a little at the top range. The high means you've gone way too far. We're about ready to bust something here. It's an emergency. So usually you see a differentiation like how many highs you have. More than 1 high or more than 1 low usually means that you have an emergency situation on there. Whereas a single high or low just indicates you're at the end of a range. Shouldn't be there, but you're there. And that's more what it's used for. Sometimes you just see a single high used as a trigger to say, okay, now it's time to levels high, start reducing it. The high means levels high and we're about ready to overrun the tank. That'd be a case of that. Flow indicating transmitter, that's where you have, not only do you have a flow meter that sends a signal back to the controller, but it also has a little indicator on top of it that you can read to see what's the flow rate. Those type of things.
President,
Yes.
I wanted to ask you, so are those identification letters specific to the company or are they universal?
These are pretty much universal. Right. I say pretty much universal. Your company may have something different. Now the very common ones like flow, pressure, level, temperature, those are, for the first letter, those are universal. Right? V for valve is, as a second letter, is typically universal. Now if you see V for the first letter, velocity is a typical one, but viscosity could be one as well. Viscosity, thickness of oil versus velocity for movement. Which is it? The ISO standard actually uses that for viscosity. But if your company doesn't worry about oil thickness, it worries about velocity of projectiles, it's going to use that V for velocity. Companies can modify this any way they want to. A good example is the Y used for the IP converter. We've seen a couple of examples here. I'm always caught by that because I've seen Y for general. In fact, you can't see it here, but this is a bunch of letters. Y, user's choice.
Yeah.
User's choice means the company decides what Y is going to mean. Now, Y can be used for a computer, Y can be used for an IP converter, Y can be used for some sort of analysis machine. It's a variety of things. That you will have to know by the company's contacts. X here is undetermined, unclassified. User's choice versus unclassified, you know, I'd be hard pressed to see what the difference is. NO, user's choice. Interesting, P is pressure or vacuum. Q, quantity or event. So even K, time or schedule. You would think T would be time, but T is used for temperature, so you do time. ISO says use letter K, but your company may use that for something else, in which case then something else would be time, if that were a concern. So these are going to be defined. As I said, like the GlaxoSmith, we had one of their bottling machines here years back, and their entire tag was nothing but numbers, no letters at all. It was about 8 digits. I stared at it to figure out what that meant. And I could pick out loop, I could pick out some instruments, just by looking at the various tags around there to say, okay, this is a loop, so what's the common? And I think the loop number was about, I want to say it was 4 digits, but there's 3 main digits that look like a 4th modifying digit somehow. Not sure about that, but the other digits in there, I could pick something out, I think for valves, I saw enough valves, but there are other things I couldn't pick out because there weren't enough examples. You really have to have a company handbook to tell you what this means. But I mean, in general, ISO is usually what people usually train on because it's more likely what you see. Our tags out there are pretty close to the ISO standard. Most companies aren't this close. It's an excellent question, really, because it's that, you know, you'll sit there with LTs here or something like that, and think, oh, hell, everybody uses LT there. You go out in your company and say, that doesn't, Mr. Nolan said, I meant that. He's full of crap again.
Yeah.
And, you know, in that context, yes, it would be.
Yeah.
But it is, you know, there are differences. The symbols can differ quite a bit too on company diagrams. You do really have to get used to what your company does, and which means when you change jobs, yeah, you flush it again. More of the drawings. This seems pretty common. It's your field, your single line, which is your primary location. Basically, your control panel is really the way you think of it. Auxiliary locations, your double lines. And your typical PLCs, your computer. So this follows the normal standard diagram, and that people don't really vary too far off of. Symbols like, let me get this zoomed in here. Circle EAT, analyzer, transmitter, AND gate, a pitot tube, drawing in there. That's behind a control panel, which makes sense, obviously. Correcting element, kind of like a yield sign, triangle. Diaphragm motor. Let's see, a double instrument in here. These, it's flow control, FC, that makes sense, FC, that's the tags in there. Flow nozzle meter, you wouldn't expect to see a shape like this necessarily, but there it is. So there are some different things in here. Flow meter, I'm not sure exactly what that does. Looks like it works off Venturi process. But there are symbols like this is a flow meter here. That shows a couple lines there, and that's a pretty fancy flow meter. I would think most diagrams wouldn't have it quite this fancy. Now you get around to the symbols, that's for the instruments mounted on there. You'll see pumps are way different. Get back to 5% here. So there you go, typical flow meter here, and all the instruments it could be. You have a sensor head for flow, transmitter, the electronics for generating the flow here. Indicator built onto it as well. So it's going to have a lot of tags. Notice you have three instruments in one, a sensor, transmitter, and an indicator all built into one. So the transmitter section is this. Indicator controller, so this must be the head part, the sphere. And that's an alarm system into that. Fluid equipment, this is separated from here, if you can call it separated, that's a bolted flange. So that's what separates the sensor from this transmitter controller, and there's a controller head here as well. Now this is a shared instrument, which is why you have this rectangle around this part of it. So it's a mixture in there to look at. As I said, some of the stuff kind of blends. It's one of the things you have in this diagram, but it shows that, you know, these are simple instruments that could have a couple tags hanging off of them. And that's probably a good place to stop. Now, talk a little bit more about this, wrap it up next week. I do want to spend a little bit more time than normal on PNID, because this is a big part of it. Then talk about individual devices and really get into the loops later on, which is where I want to spend a little bit more time than normal, because again, it's a subject that is not well done in Amatrol. But I wanted to at least show the effect of loops and calibration where it all fits in.